6:17 a.m., September 3rd, 1894. William Hasbrouck was standing 9 feet from his separator when the flywheel rim fractured. A section of cast iron weighing 43 pounds struck him in the chest at an estimated velocity of 62 feet per second. He died before his body hit the ground. Hasbrouck owed $840 on the steam traction engine. His farm was worth $1,200. His widow sold it for $900 to cover the debt. What eventually made these machines safe was a metal band weighing 11 pounds installed around the rim that nobody thought to patent until 31 farmers were already dead. The 1890s saw American agriculture mechanize faster than any decade before or since. Between 1890 and 1899, manufacturers sold 41,000 steam traction engines into American farmland. Auger Case sold 9,200 units. Advanced Rumilly moved 6,400. Huber Manufacturing shipped 4,100. Russell and Company sold 3,800. Altman Taylor moved 2,900. Every catalog promised the same thing: faster threshing, smaller crews, more acres covered per day. The promotional materials showed clean machines on level ground with crews of 4 men in pressed shirts standing at safe distances. Nobody mentioned that flywheel rims were failing in the field at a rate that would eventually kill 127 documented farmers between 1891 and 1903. The flywheels on these machines were not small. A typical separator flywheel measured 8 feet in diameter. The rim alone weighed between 200 and 300 pounds, and cast in sections and bolted together. The wheel spun at 180 to 220 revolutions per minute during normal threshing operations. At that speed, the outer edge of the rim was traveling at approximately 47 miles per hour. When a section of that rim fractured and separated, it became a projectile carrying enough kinetic energy to kill it 30 yards. The engineering principle was sound in theory. Cast iron flywheels had been used in stationary steam engines for decades without widespread failure. But stationary engines ran on factory floors with constant speeds, regulated temperatures, and professional engineers monitoring bearing wear and shaft alignment. Steam traction engines operated in wheat fields. They ran 14 hours a day in July heat. They were moved across uneven ground while still under load. The frame flex from field operation created stresses the original design never anticipated. The wheel rims developed internal fractures that were invisible from the outside until the day a section separated at full speed. The first recorded fatality was Henry Maltsby, killed near Chillicothe, Missouri on August 14, 1891. The coroner's report listed cause of death as blunt force trauma to the head and chest. The manufacturer, Huber Manufacturing, sent a field representative who examined the remains of the flywheel and concluded that Maltsby had been running the engine above the recommended speed. The widow received no compensation. The farm was sold at auction 4 months later. 3 more men died in 1892. Joseph Kellner near Des Moines on June 22nd. Near Frank Hobart outside Lincoln, Nebraska on July 9th. Samuel Pritchard in southern Illinois on August 1st. Each time, the manufacturer examined the wreckage and concluded operator error. Kellner had allegedly failed to maintain proper lubrication. Hobart had supposedly overloaded the separator. Pritchard had run the engine with a misaligned belt. In each case, the flywheel rim had fractured and separated. In each case, the manufacturer blamed the dead man. By 1894, the pattern was impossible to ignore. 13 men died that year from flywheel failures. The deaths were geographically scattered: Indiana, Iowa, Kansas, Nebraska, Illinois, Ohio, Missouri. Different manufacturers, different engine sizes, different crew sizes and experience levels. But the mechanism was identical. During normal threshing operations with no warning, a section of flywheel rim would separate and strike someone in the immediate area. The fragment would travel between 15 and 90 feet, depending on the angle of separation. Death was usually instantaneous. Injuries were catastrophic. There were no cases of minor wounds from flywheel failures. You were either untouched or you were dead. The manufacturers issued new operation manuals. Russell and Company published a 12-page supplement in March 1895 titled Proper Care and Feeding of Steam Traction Engines. Page 7 contained 3 paragraphs about flywheel inspection. Operators were instructed to examine the rim for cracks before each day's operation. The manual did not explain what a dangerous crack looked like. The fractures that led to separation were internal, caused by repeated thermal cycling and frame flex. They were not visible on the surface until seconds before failure. JMI sent field representatives to major agricultural shows with demonstration units. The representatives gave lectures on proper engine operation. They emphasized the importance of maintaining steady speeds, avoiding overload, and conducting regular inspections. They did not mention that Case engines had been involved in 9 of the 13 deaths in 1894. When asked directly about flywheel safety, the representative stated that properly maintained equipment posed no danger to trained operators. The engineering reality was that cast iron flywheel rims on mobile engines were failing at a statistically predictable rate regardless of operator behavior. The material could not withstand the combination of high rotational speed, thermal cycling, and frame flex from field operation. Every hour of operation added microscopic internal fractures. Every temperature change expanded and contracted the metal at different rates than the hub and spokes. Every bump crossing a field transmitted shock loads through bearings that were never designed for lateral stress. The rim was failing because the design was wrong for the application. But admitting that would have required recalls, retrofits, and liability for deaths that had already occurred. 16 men died in 1895. 21 died in 1896. The agricultural press began publishing the deaths as a regular column. The Prairie Farmer ran a monthly feature titled Threshing Accidents that listed names, dates, locations, and known details. By mid-1896, the pattern was clear to anyone reading the reports. Flywheel failures were killing experienced operators and new hands at the same rate. They were killing men working for manufacturers' demonstration crews. They were killing mechanics who had built and maintained steam engines for 20 years. Experience was not protective. Training was not protective. Careful operation was not protective. The wheels were failing because the wheels were going to fail. The Illinois State Board of Agriculture commissioned an investigation in October 1896. They assigned the work to Martin Hendricks, a mechanical engineer who had designed stationary steam engines for the Corliss Steam Engine Company before moving to agricultural equipment. Hendricks was given access to 12 wrecked engines whose flywheels had failed during the 1896 season, and he was authorized to interview survivors and examine coroner's reports from 17 deaths across Illinois, Iowa, and Indiana. Hendricks submitted his report on February 3, 1897. The document was 41 pages. It was published in the Journal of the Illinois State Board of Agriculture in March 1897. The core findings were technically correct. Hendricks identified that the failures were occurring in the rim sections, not the spokes or hub. He documented that fractures initiated on the inner surface of the rim where it joined the spokes. He correctly calculated that the stress at that junction point was exceeding the tensile strength of the cast iron under field conditions. He recommended that manufacturers switch to steel flywheels, which had approximately 3 times the tensile strength of cast iron. What Hendricks missed was that switching materials would take years and require completely new casting patterns, new machining processes, and new inventory systems for every manufacturer. There were already 38,000 steam traction engines operating in American fields with cast iron flywheels. A material change would not protect a single one of them. Hendricks had correctly diagnosed the root cause but proposed a solution that was economically impossible to implement fast enough to prevent the next 100 deaths. The report also failed to identify the immediate mechanism that turned an internal crack into a catastrophic separation. Hendricks assumed the rim failed gradually, developing visible cracks that operators should have been able to detect during inspections. He did not understand that the failure was instantaneous. The internal crack would propagate completely through the rim thickness in less than 1 revolution of the wheel. By the time any crack was visible from outside, the rim section had already separated and was in flight. Manufacturers responded to the Hendricks report by announcing their commitment to improved quality control and casting processes. Advance Rumely published a full-page advertisement in the American Thresherman in April 1897, stating that all new flywheels would be inspected using a new percussion testing method that could detect internal flaws. The advertisement did not mention that the testing method could only detect flaws larger than 1/4 inch in diameter. The fractures that led to failures began as microscopic cracks. 19 men died from flywheel failures in 1897. The death toll was lower than 1896, high but not because of any safety improvement. The 1897 wheat harvest was poor across the Midwest. Less grain meant less threshing. Fewer operating hours meant fewer opportunities for wheels to fail. If you want to understand how an 11-pound metal band solved a problem that killed over 100 men, and why it took 31 deaths before anyone thought to install something so simple, keep watching. The answer involves a detail so obvious that every trained engineer missed it, but a farmer who barely finished 8th grade saw it instantly the first time he examined a failed wheel. And if this kind of forgotten story matters to you, hit subscribe now. These are real documented deaths that almost nobody remembers, and the only way this kind of history stays visible is if people like you decide it is worth preserving. The farmer was named Albert Cuthbert. He operated 240 acres outside Hastings, Nebraska. He owned a Russell & Company steam traction engine that he had purchased new in 1893 for $1,400. He still owed $620 on it in August 1897. Cuthbert had a younger brother named Raymond who worked his own quarter section adjacent to Albert's land. The brothers often ran threshing crews together, alternating between their two farms and then hiring out to neighbors for the rest of the season. On August 9, 1897, at approximately 2:30 p.m., Raymond Cuthbert was standing 11 feet from the separator when the flywheel rim on Albert's Russell engine fractured. A section of rim weighing 38 pounds struck Raymond in the lower back and right hip. Near to the impact severed his spine and fractured his pelvis in 4 places. He was conscious for approximately 6 minutes before he died. Albert was the only person with him when he died. The nearest doctor was in Hastings, 14 miles away. By the time Albert got Raymond into a wagon, his brother was already gone. The county coroner listed cause of death as catastrophic internal bleeding due to blunt force trauma. The coroner noted in his report that the deceased had been standing at what should have been a safe distance based on standard operating procedures published by the manufacturer. Albert Cuthbert paid for the funeral. It cost $87. 143 people attended. Raymond had not been married. His quarter section went to Albert, and who now owned 440 acres and owed $620 on an engine he refused to start. Albert Cuthbert did not sleep for the first 4 nights after his brother died. On the 5th day, he went back to the field where the engine was still sitting and began examining the flywheel. The section that had separated was lying in the stubble 41 feet from the engine. Cuthbert picked it up and carried it back to his barn. He spent the next 3 days studying how the rim sections were attached to the spokes and to each other. He was not an engineer. He had finished 8th grade in a one-room schoolhouse. He had never taken a mathematics course beyond basic arithmetic, but he understood how things broke. What Cuthbert realized was that the engineers had been trying to solve the wrong problem, and Hendricks and the manufacturers were focused on preventing cracks from forming in the cast iron. Cuthbert understood that preventing the cracks was impossible. Cast iron under those stresses would always develop cracks eventually. The solution was not to prevent cracking. The solution was to prevent a crack from becoming a separation. The rim sections were bolted together at their ends. Each joint used 4 bolts. The design assumed that if the rim cracked, the crack would develop slowly enough that an operator would see it during inspection, and the rim could be replaced before the crack propagated through the full thickness. But that assumption was wrong. When a crack reached critical length, it propagated through the rim in a fraction of a second. By the time the crack had opened enough to see, the section had already separated and was no longer restrained by the bolts at the joints. Cuthbert's insight was that the rim needed continuous restraint around its entire circumference, not just at the bolted joints. If you could prevent the rim from expanding outward when a crack opened, The section would not separate even after the cast iron had fractured completely through. The crack might propagate, but the fractured section would be held in place by external force, not by the strength of the cast iron itself. He designed a steel retaining band. It was a continuous hoop, slightly smaller in diameter than the flywheel rim, that would be heated, slipped over the rim, and allowed to cool. As the steel cooled, it would contract and grip the rim with continuous radial pressure. If a section of rim cracked, yet the steel band would prevent it from moving outward. The fractured section would be held in place by the band until the operator could stop the engine and discover the crack during inspection. Cuthbert could not manufacture the band himself. He took his drawings to Hastings and met with the owner of a machine shop named Frederick Walsh. Walsh looked at the drawings and understood immediately what Cuthbert was proposing. Walsh said he could fabricate a band from half-inch steel plate rolled into a hoop and welded. The band for Cuthbert's 8-foot flywheel would weigh approximately 11 pounds and cost $9 to fabricate. The first test installation occurred on September 18th, 1897 at 7:15 a.m. in the field behind Cuthbert's barn. Walsh had delivered the band 2 days earlier. Cuthbert and Walsh heated the band with a wood fire until it expanded enough to slip over the rim with approximately 1/8 inch of clearance. They held it in place with iron hooks while it cooled. The cooling process took 46 minutes. When they removed the hooks, the band remained in place, gripping the rim tightly enough that Cuthbert could not move it by hand. Cuthbert started the engine at 8:02 a.m. He ran it unloaded for 30 minutes, then connected it to the separator and ran it under load for 2 hours and 17 minutes. The band remained in place. The engine operated normally. There was no measurable vibration or noise that had not been present before installation. The band was still on the flywheel when Cuthbert died in 1934. He ran that engine for another 11 seasons after his brother's death, and the cast iron rim developed 3 visible cracks during those years. Cuthbert documented each crack in a journal he kept in the barn. The first crack appeared in 1899. It was approximately 3 inches long, located in the rim section directly opposite the band weld. The crack was visible on the outer surface, but had not propagated through the full thickness. Cuthbert continued operating the engine. The crack did not extend, the section did not separate. The second crack appeared in 1902. It was 4 inches long, located 2 sections away from the first crack. Again, the crack did not propagate, and the section did not separate. The third crack appeared in 1907. It was 2 inches long. The rim section remained intact. Cuthbert showed the banded flywheel to neighbors. By harvest season 1898, and 6 other farmers in the Hastings area had installed similar bands, all fabricated by Walsh. None of those engines experienced rim separations. Word spread through informal networks. By 1899, machine shops in Nebraska, Iowa, and Kansas were fabricating retaining bands based on descriptions from farmers who had seen Cuthbert's engine. Then men started dying again. Between March and September 1899, 7 farmers were killed by flywheel failures on engines that had been fitted with improvised retaining bands. The bands had failed. In each case, investigators found that the band had been made from material that was too thin, too brittle, or improperly welded. Some bands were made from iron instead of steel. Some were made from 1/4-inch plate instead of 1/2 inch. Some were installed without being properly heated and allowed to contract, and so they had insufficient grip pressure on the rim. The worst failure occurred on July 22, 1899, near Council Bluffs, Iowa. Thomas Ridgway had installed a band fabricated from 3/8-inch iron plate. The band fractured during operation and separated into 2 pieces. One piece wrapped around the flywheel spoke and jammed the wheel, causing the belt to the separator to tear loose. The loose belt struck Ridgway across the face and neck. He died from a severed carotid artery. His crew managed to stop the engine, but Ridgway was dead within 2 minutes. He left a wife and 5 children. The farm went to auction. The family moved to Omaha, where his widow worked in a laundry. The improvised bands were failing because farmers and small machine shops did not understand which aspects of the design were critical. And the material had to be steel, not iron, because steel had the ductility to absorb sudden shock loads without fracturing. The thickness had to be at least half an inch because thinner material did not have enough mass to contain the energy of a separating rim section. The band had to be installed with shrink fitting because a loose band could rotate independently and develop fatigue cracks at the weld. Cuthbert published a letter in the Nebraska Farmer in October 1899 explaining the exact specifications for the band. He listed material type, thickness, heating procedure, and installation method. He explained why each specification mattered. He included a warning that bands made from incorrect materials or installed incorrectly would fail and could make the flywheel more dangerous than it had been originally. Frederick Walsh published a similar letter in the American Thresherman in November 1899. Walsh included material specifications and fabrication procedures detailed enough that any competent machine shop could replicate the design correctly. Walsh did not charge for the information, neither did Cuthbert. Neither man patented the retaining band. By the end of 1899, correctly fabricated bands were being installed on steam traction engines across the Midwest at a rate of approximately 60 per month. The installation cost varied between $7 and $14 depending on flywheel size and local labor rates. For farmers who already owned engines, that was a manageable expense compared to the $1,200 to $1,600 cost of the original equipment. For manufacturers, the situation was more complicated. Russell and Company's internal correspondence from late 1899 shows that company engineers had evaluated the retaining band design and concluded it was effective. A memo dated November 14, 1899, written by Chief Engineer Howard Lansing, stated that shrink-fitted steel bands would effectively prevent rim separation and that the company should consider installing them as original equipment on new engines. The memo included a cost estimate. Manufacturing and installing bands on new engines would add $6.30 to the production cost per unit. Retrofitting the existing installed base of approximately 3,800 Russell engines would cost approximately $24,000 in materials and labor. Russell and Company's profit margin in 1899 was 11%. The company sold 1,047 engines that year at an average price of $1,427. Total revenue was approximately $1,495,000. Profit was approximately $164,000. A $24,000 retrofit program would consume 14% of annual profit. The company did nothing. J.I. Case's internal analysis reached similar conclusions. A report dated December 3, 1899, calculated that retrofitting approximately 9,200 Case engines in service would cost approximately $60,000. The report recommended against voluntary retrofit. It noted that the company had won several legal cases defending against liability claims by arguing that operators had failed to maintain equipment properly. The report stated that offering a retrofit program could be used as evidence in future litigation that the company had known the original design was defective. Advance Rumely's chief engineer wrote a memo in January 1900 recommending that new engines be equipped with retaining bands at the factory and that the company offer retrofit kits for sale to owners of existing equipment. The retrofit kits would be sold at cost, plus 15%. The recommendation was rejected by the company president, who noted that most farmers had already installed bands fabricated by local shops, and that offering retrofit kits would generate minimal revenue while implying that the original design had been unsafe. The standoff continued through 1900 and 1901. Deaths from flywheel separations dropped to 3 in 1900 and 2 in 1901, but only on engines that had not been retrofitted with bands. Engines with properly installed bands experienced 0 rim separations. The data was clear. The solution worked. The manufacturers did nothing. What broke the standoff was the death of Edward Pritchard on June 14, 1902. Pritchard was not a farmer. He was a demonstration engineer employed by J.I. Case. He was operating a Case steam traction engine at the Ohio State Fair in Columbus. The engine was 2 years old. It had been maintained according to factory specifications by factory-trained mechanics. At 3:47 p.m., during a demonstration run in front of an estimated crowd of 800 people, the flywheel rim fractured and a section separated. The section traveled 53 feet and struck Pritchard in the chest. He died instantly. The section continued past Pritchard and struck a spectator, a schoolteacher named Margaret Hollis, in the left leg. Her leg was amputated above the knee. She survived. The Columbus Daily Dispatch ran the story on the front page. The headline was "Case Engine Kills Operator at State Fair." The article included witness statements from 11 spectators. All 11 stated that the engine had been operating normally with no visible signs of distress or malfunction. Several witnesses noted that this was the same type of failure that had killed dozens of farmers over the past decade. One witness was quoted saying that farmers had solved the problem years ago with steel bands and asking why the company had not installed them. J.I. Case announced a voluntary retrofit program on July 2, 1902. Yet the company offered free retaining bands to all owners of Case steam traction engines manufactured between 1890 and 1902. Installation would be performed at no charge by company service representatives or at authorized dealers. The company published the announcement in every major agricultural newspaper in the United States. The announcement did not admit that the original design had been defective. It stated that the company was offering the retrofit in the interest of improving operator confidence and reflecting the latest advances in flywheel safety technology. Russell and Company announced a similar program on July 9th. Advance Rumely followed on July 15th. Huber Manufacturing on July 22nd. By the end of August 1902, every major manufacturer of steam traction engines had announced retrofit programs. The programs were structured as voluntary customer service offerings, not as recalls. No company admitted liability. No company offered compensation for deaths that had already occurred. Installation of factory-supplied retaining bands began in September 1902 and continued through the spring of 1904. Company records show that approximately 28,000 engines were retrofitted during that period. The actual number was likely higher because many farmers had already installed bands fabricated by local shops and did not participate in the manufacturer programs. The last documented death from a flywheel rim separation on a steam traction engine occurred on August 3, 1903. The victim was Isaac Drummond, killed near Salina, Kansas. Drummond was operating a 14-year-old Advance Rumely engine that had never been retrofitted. The coroner's report noted that the flywheel had no retaining band installed. The total documented death toll from flywheel failures between 1891 and 1903 was 127 men. After retrofit band installation became standard, the death rate from flywheel failures dropped effectively to zero. Between 1904 and 1920, when steam traction engines began to be replaced by gasoline tractors, there were 3 recorded deaths attributed to flywheel failures. All 3 occurred on unmodified engines more than 15 years old. There were no recorded failures of properly installed retaining bands during that period. The principle that Albert Cuthbert discovered is called mechanical redundancy. Instead of trying to prevent a component from cracking, you design a secondary system that contains the failure even after the primary component has failed completely. The primary structure is the cast iron rim. The secondary containment is the steel band. The rim can crack and even fracture completely through, but the band prevents the fractured section from separating and becoming a projectile. That same principle is used in every modern rotating system that operates at high speed with potential for catastrophic failure. Industrial flywheels today use composite materials for the rim and steel containment bands or shells that surround the entire wheel. If the rim fails, the containment system absorbs the energy and prevents debris from escaping. Gas turbine engines use similar systems. The fan and compressor blades are the primary structure. The engine case is designed to contain a blade if it separates from the rotor. The case is not intended to prevent blade failure. It is intended to prevent a failed blade from penetrating the case and hitting something outside the engine. The Federal Aviation Administration requires that all turbine engine cases be tested by deliberately failing a blade at full speed and verifying that the case contains the debris. The test is called a blade-out test. It is required for engine certification. The principle is identical to what Cuthbert designed in 1897. You assume the primary component will fail. You design containment that works after failure has occurred. Albert Cuthbert farmed his land until 1929 when he leased it to a neighbor and moved into Hastings. He died on February 11, 1934 at age 71. The obituary in the Hastings Tribune listed him as a retired farmer. It did not mention the retaining band or his brother's death, or the fact that his design had likely saved hundreds of lives. 86 people attended his funeral. He was buried in the Hastings City Cemetery, 3 plots away from his brother Raymond. Cuthbert never patented the retaining band. Frederick Walsh never patented the manufacturing process. The design was published freely in agricultural newspapers and copied by machine shops across the country. Neither man made any documented profit from the invention beyond the $9 Walsh charged Cuthbert for fabricating the first band. The original banded flywheel from Cuthbert's Russell engine was donated to the Hastings Museum in 1947 by Cuthbert's niece. It is currently in storage, not on public display. The wheel is 8 feet in diameter. The rim sections show 3 visible cracks, none of which propagated to separation. The steel retaining band is still in place. It shows surface rust, but no structural deterioration. The band weighs 11 pounds and 2 ounces. It is made from half-inch steel plate, rolled into a continuous hoop with a single welded joint. The weld is still intact. If you have family stories about steam traction engines or early farm equipment, leave a comment. If your grandparents or great-grandparents operated this equipment, mention where they farmed. If you know of similar safety inventions that came from farmers instead of engineers, share what you know. Name your state or region in the comments so we can see where these stories are still remembered. And subscribe if you want more forgotten agricultural history that almost nobody talks about anymore. These stories only survive if somebody decides they are worth preserving.